Okay, and then for the magnetic circuit with the DC excitation, okay, there are two basic problems to consider for the analysis of the magnetic circuit with DC excitation. Okay, so the first one, okay, with the given flux, you have to determine the currents required to produce it. And then the next problems is with the given current, you have to compute, okay, the flux produced. So this is two basic problems, okay, that we need to consider, okay, in analyze, okay, the magnetic circuit with the DC excitation. Okay, so for the source of magnetic flux or MMF, okay. Okay, so what is MMF? Okay, so the current through the coil creates magnetic flux. Okay, when you have a current, okay, through the coils, it creates the magnetic flux. Okay, so the greater or the number of turns, okay, the greater will be the flux. So you have more number of turns, okay, in the coils, okay, it will give you more flux. Okay, so this flux producing ability of the coil, okay, so it's called as a magnetomotive flux or MMF. Okay, magnetomotive force, sorry, or MMF. Okay, so the symbols, okay, is F, and the unit is ampere turn or AT, which this F is equivalent to the number of turns, okay, times with the current in the coil. Okay, so means from this formula you can see, okay, this F or this MMF, it is proportional, okay, with your number of turns times with your currents. Okay, if you increase, okay, the number of turns, so you will get greater MMF. Okay, and then what is the reluctance? So this is all the, okay, the properties, okay, that you will see inside your magnetic flux or magnetic circuits. Okay, so reluctance, which is with the italic, okay, represented by the italic R, okay, is the opposition to the magnetic flux. Okay, so the flux in magnetic circuit also depends on the opposition of the circuit present to it. Okay, the term is reluctance. Okay, depends on the dimension of the core and the material which it is made. Okay, so if you have, okay, magnetic circuits, okay, so this magnetic circuit will come, okay, or will exist, okay, from the different, okay, types of magnetic materials, okay, so they have the difference in reluctance, and also which depends on the dimension of the core. Okay, so the symbol of R, okay, so it represented by the italic R, and the unit is ampere turn per Weber. Okay, and then like a resistance of the wire. Okay, so previously, okay, we see on the circuit analysis, we have the resistance, right, inside of the wire. So same with these magnetic circuits. So we have the reluctance, okay, which oppose, okay, with your to your magnetic flux. Okay, so like a resistance of the wire, reluctance is directly proportionally to length and inversely proportional to the cross-sectional area. Okay, so in mathematical form, okay, so this reluctance, okay, for these magnetic, okay, circuits, okay, is equivalent to, okay, L divided by mu times A. Okay, the length divided by permeability times with your area or cross-sectional area in meters squared. Okay, which also equivalent to the MMF divided by V of flux. Okay, and the unit is AT per Weber or ampere turns per Weber. Okay, so this is the reluctance. Okay, so where your mu, okay, your permeability, okay, is equivalent to mu naught times with your mu R. Okay, so this relative, okay, relative permeability or mu R, okay, depends on the materials. Okay, so mu R is equivalent to 1 for the non-magnetic materials. Okay, the relative materials, okay, you can refer to the tables given. Okay, so the mu naught, okay, is given as 4 pi times 10 power of minus 7. Okay, so the multiplication of mu naught and mu R will give you the mu. Okay, the permeability is a measure, okay, of how easy it is to establish flux in the materials. Okay, so ferromagnetic materials have the high permeability, which give you a low reluctance, while the non-magnetic materials have the low permeability, okay, which has a high reluctance. Okay, so the Ohm's law for the magnetic circuits. Okay, so the relationship between the flux, okay, MMF and the reluctance, okay, is given by this formula. So the flux is equal to MMF, okay, or F here divided by reluctance. Okay, so you can see the relationship is similar to the Ohm's law, which depicted symbolically as following. Okay, so you have the F here. Okay, so in Ohm's law you have the V right here. Okay, the flux here. The flux can represent in your electric circuits is your I. Okay, so this is in your electric circuits is your resistance, right? So, but for the magnetic circuit is represent the reluctance. So this is the V, this is the I, and this is the R. Okay, but for the magnetic circuit, okay, we follow the Ohm's law. Okay, so this is the F, the flux, and the reluctance. Okay, and then we go to this example 2. Okay, so you have the coil width 300 turns, okay, and the I give you 0.5 ampere. Okay, so from the right hand rules, okay, so you have the flux here, okay, which flowing through your coil. Okay, for the flux above, if the reluctance of the magnetic circuit is equivalent to 12 times power of 4, okay, ampere turns per Weber. So what is the flux in the circuits? Okay, so using the previous formula, right? The F is equal to N I. Okay, so you put N with 300 turns. Okay, and the I is given as 0.5 ampere. So you will get the F is 150 ampere turns. Okay, and then the flux is F divided by R. Okay, so which give you 150 ampere turns divided by your flux, your reluctance, is equivalent to 12 times power of 4. Okay, and then the flux is getting at 12.5 times 10 power of minus 4 Weber. Okay. Okay, for the magnetic field intensity and magnetization curves. Okay, so magnetic field intensity, also represented by H, is a measure of the MMF per length of the unit. Okay, so the H here is the F. Okay, the F is MMF, right? Okay, divided by the length, which also, because we know the F is equal to N times with your I, right? Okay, divided by L. And the unit is ampere turns per meter. Okay, is also known as the magnetizing force. Okay, so if we rearrange the equation, so we can find the N is equivalent to HL. Okay, from here, we get the N equivalent to HL. Okay, in ampere turns. Okay, so in using the electric circuit analogy, the Ni is a product of MMF here. Okay, because the F is equal to Ni. Okay, while the H times L product is the MMF drops. Okay, the drops mean if you have in electricals, this is your right? This is your IR, the drop. V is equal to IR here. Okay, so same with this one. The H times with your L is equal to MMF drop. So the HL is a drop. Okay, the NI is your source. Okay, so this, okay, this analogy, so-called the Ampere's second law. Okay, and then the relationship between the B and H, the flux density and the flux intensity. Okay, the B is the flux density. Okay, the H is the flux intensity. Is equivalent. The B, the flux density is equivalent to the permeability times with your magnetic field intensity. So where your mu is the permeability of the core. Okay, so what is magnetization curve? Okay, magnetization curve is also the BH curve. Okay, it's familiar, okay, known as the BH curve. For the ferromagnetic materials, mu is not constant, okay, but varies with the flux density, and there is no easy way to compute it. Okay, so a set of curves called the BH curve or the magnetization curve is the same curves, okay, provide information about the B and H, okay, properties. So a separate curve required for each material. So this is the curve. Okay, the magnetization curves, or also called as a BH curve. So you have the, okay, the graph here. Okay, the curve give you, okay, the B, okay, the B or the flux density, okay, versus with your H, the flux intensity, okay, respective to the different, okay, ferromagnetic material, okay, which, okay, present here as which present the graph of cast iron, okay, cast steel, and also sheet steel. Okay, so they have different properties, okay, for the B and the H. Okay, so in example 3 here, okay, so if B is 1.4 Tesla for the sheet steel, okay, the materials is from the sheet steel. So what is your H? Okay, so now, okay, from the BH curve for the sheet steel curve, okay, as we refer to the sheet steel curve, okay, so your B is given as 1.4, right? Okay, and then, okay, we take this 1.4, okay, to see, okay, the properties for the H for the sheet steels. Okay, so it gives you, okay, let's refer to this graph, okay, the H, okay, is obtained at 1000, okay, ampere turns per meter. Okay, so for the B is equal to 1.4, okay, we project, okay, to the respective H, so it gives you the H at 1080 per meter. Right, you see, right? Okay, so we then, okay, I stop here and then we proceed to part C. So thank you for your listening.